So in this lecture, we discuss on different type of recurrent state. So to do this, so we first find the average number of. So what will be the average number of visit to a recurrent state? So is assume that it is a recurrent state. So it is visit with probability 1. But what is the average number of visit? So average number of visits to a recurrent state. Now, is the indicator random variable like that? One z with y is a element of the state space. It is either 1 or 0. If z equal to y, then 1, z equal to y, then it is 0. So remember, z is a random variable, so it is a 1 y is also random variable. So what will be the expectation of this random variable? This is interesting. So this is a Bernoulli random variable basically. This is a Bernoulli random variable. Now it is starting from x. E suffix x means it is starting from x. What will be the random variable this? So it is 1 or 0. So it is a Bernoulli, Bernoulli 1 0, and with the this basically this is a Bernoulli random variable. And with the success probability of 1 is just probability of z equal to y. So probability of z equal to y is a success probability. That means when z equal to y, then the random variable takes value 1. So what is the expectation of the Bernoulli random variable? We know the expectation of Bernoulli random variable is just p, the success probability. So it is just probability of, here it is we use xn. So it is xn equal to y, but it starts from x. It is conditional thing. So it is starting from x. The xn is y. This probability is expectation of this random variable starting at x. Now, what is this? You start from x, is reach at y at n steps. That means it is n step transition function, probability function from x to y. So this expectation with respect to this random variable is very important. We let us see that why this we use this random variable. Now set ny. So n at y is just sum over m equal to 1 to m equal to 1 to n, that indicator random variable. That is important. We use one indicator random variable, that summation over that indicator random variable from m equal to 1 to n. This is important. This is useful. Why? Because this is linearity. This expectation is a linearity. Expectation of x plus y equal to expectation of x plus x plus y. That's why we use this thing. We will use the linearity of the expectation. Now, what is g n x y? We use the g n x y is that sum over m equal to 1 to n, the m step transition function from x to y, and that is nothing but expectation of, this is sum over the expectation, sum over the expectation for that xm. Now we know that is by linearity, this is sum over expectation over the sum. That is important. That's why we use this notation, identity random variable, indicator random variable. So, and what is this? This is just ny. So it is just expectation of x in ny. So it is the expected number of visit of the chain to y. What is this? This is the expectation number of visit. So it is ny is the sum over all this thing. So it is expected, and this gnxy is the expected number of visits of the chain 2y. Why it is so? Because it is just expectation of that number. Number means that 1ym. Remember what is 1ym? This is if it is 1 if xm is y. So that say n equal to 10. So this is sum of that 1y(x1) plus 1y(x2). And what is 1y(x1)? That means the first at the step 1 is visit x1 equal to y. So that means at the step one, first step, just only one step, it is visit y. Second step, it is visit y. So if it is the sum is 3, that means that for 3 m's this is 1 and for rest 7 m's it is 0. Take say n equal to 10 and say that nyy is nny is 3. That means what is the meaning of that? The 3 ones and 7 zeros. That means 3 times it visit y, and that is we have this probability for that. So that's why it is the expected number of visit. It is the expected number of visit. So it is the expected number of visit of by the chain 2y. In the n step, it is in the n step during the time n. So during times m equal to 1, 2, up to n. So it is in n times, and we have to go n tends to infinity. Then we will get the expected number of times visit for this chain for infinite long time. Now starting at x, remember that is starting at x. Now let y is a transient state. Then what happens? Let y be a transient state. Then what happens? Then if y be a transient state, then we know that limit n tends to infinity, that ny is finite with probability 1. So it's with probability 1 it is finite. For the transient state with probability 1 it is finite, for recurrent state is infinite with probability 1. And then what happens? Then limit n tends to infinity, g n, which is the expected value of that, the expectation of this quantity. So limit and expectation can be interchanged. That is the expectation of m1 ny, and this is gxy, and which is finite with probability 1. Oh, sorry. We take the expectation, so no question of with probability 1. It is for all x belongs to the state space. So with probability 1, this is true. So that means probability with probability 1, this is true. That means if you take the expectation, the expectation is this equal to this, since it is with probability 1. Now, then limit n tends to infinity, nyy divided by n, it is 0, because this limit is finite. So this is 0 with probability 1, that expected number of that, the average number of visit. And we have what we have again, this limit n tends to infinity, the expectation also, this average number of expected visit, that is this is 0, because this limit tends to, the limit of the numerator tends to is a finite number. So for all x belongs to a state space, if y is a transient state, so starting from x, or whatever the y x may be, the expected number of visit during the n time divided by n, that tends to limit n tends to infinity, that tends to 0, because the expected number of visit during the time n, it is actually finite for all. That limit is also finite. That is not, that is obviously that is finite for n, but that limit is also finite as n tends to infinity. Now what happens for if y is recurrent state? Then that expectation must be infinite. So let y be a recurrent state. recurrent state. Now what happened? Then let my take my expectation of starting from y of ty, the hitting time of y, starting from y. What is it? It start from y and hit y, hitting time. So that expectation. So what is this denote? That denotes the mean time, mean return time. So return basically is the return. It start from y and return at y. Is mean return time. So it is average return time. So expectation of that mean return time is called mean return time to y for a chain starting at y. So start from at return time at y. Is mean return time is this small y, small m suffix y, and that is the expectation of ty. Now again we have to take one more indicator random variable. Say that random variable is like that of this. So this is taking value 0 or 1. 1 if this hitting time is finite, and if hitting time is infinite. So then it is 0. Now there is an important result on that. So theorem is this: let y be a recurrent state. We omit this proof. Be a recurrent state. The proof is complicated, so we just omit. Then limit n tends to infinity, that ny sorry, ny divided by n, that is 0 for transient state, but this is not 0 for recurrent state. It is just the hitting time for hitting time of y will be finite in that indicator and here divided by my with probability 1. This is with probability. So this is this result. The proof of this result we omit this. It's slightly complicated, and the corresponding expectation, the limit n tends to infinity, that's corresponding expectation gn xy divided by m, or it should be n, sorry, it should be n, that is equal to rho xy divided by my for all x belongs to. There is no question of with probability, it is just for all x, it is expectation. And this proof, we omit this proof, just state as a result. Now, what is the corollary of this result theorem? There is important corollary is this: let C be an irreducible closed set of recurrent state then what happened? Then limit n tends to infinity g n xy divided by n. This is rho xy is 1, so it is 1 by my for all xy belongs to the irreducible state. So rho xy is 1, and if probability of x0 starting at the probability of x0, that means change started at x0, this is in the closed irreducible closed set. If this is 1, if this probability is 1, starting in the starting phase, it is in the irreducible closed set, initial distribution fully on the initial on this C, then for all y belongs to C, that limit n tends to infinity n y by n, that is also 1 by my with probability 1. Now it is with probability 1. There is no question of expectation. The previous gxn is the expectation that ny is the random variable. The expectation of this is g of gn xy. So it is just coming from the result, the theorem for the special case. this corollary. Now we have the important concept called null recurrent and the positive recurrent. What is null recurrent and what is positive recurrent? So null recurrent. So a recurrent state is called null recurrent. A recurrent state may be null recurrent or positive recurrent. So recurrent state Y is called null recurrent if this my is infinite. It's called null recurrent. What is the meaning of that? If my is infinite, that means that limit is 0. That limit g n xy by n, that limit is 0, which is true for transient state. For transient state, this limit is 0. And for recurrent state, still it can be 0 if my is infinite. Similarly, ny by n, that limit is 0 for the transient state. And it is for recurrent state, it is 1 by my for with probability 1. But if my is itself infinite, then it is again 0. So there is in view of this nyy, that limit, the transient state and that null recurrent state behave like the same thing. And it's called positive recurrent. And y is called positive recurrent if this my is finite. So the classification of state is like transient and recurrent is not transient and recurrent. You have to again classify that recurrent state in two different recurrent state, the null recurrent as well as null recurrent as well as positive recurrent. Two different. We classify the null that recurrent state in two different state. So what is the idea that in for null recurrent state, that expected number of visit is 0 actually. That expected number of visit, that that so that sorry, that expected number of visit not 0, but divided by n, that is 0. That is 0. That limit g n xy divided by n, that limit is also 0. This is 0 for transient state, but this is 0 for non-recurrent state also. This limit is 0. This g n xy divided by n, that n tends to n, that is also 0. So it obviously it's visit that state y, but the idea is like that. So its visit average number of visit for 10 in 10 n equal to 10 in 10 steps, say it is 1. So it is 1 by 10. So in 100 step it is not 10, it is say 2. It's a 1000 step, it is a 3. So it is like a n by 10 to the power n. So that means it is 0. That limit is 0. The ratio of this is 0. The number of visits divided by n, that is 0. That is the idea of null recurrent and positive recurrent. So if y is null recurrent, then what happens? Then we have this limit n tends to infinity g n xy by n, that limit is 0. That is same as limit n tends to infinity. This is just sum over all this transience thing, and that transition probability, sum over all this transition probability from x to y in m step for m equal to 1 to n, divided by that n, this is 0. So what we prove actually for the null recurrent state, that somewhere all this transition probability from m steps transition probability from x to y divided by n, that is 0. Obviously these are all probability, and that probability must be, the sum must be less than n, but limit may not be 0, but in non-recurrent this is 0. Actually more strong result can be proved, one stronger result without any proof, we just state one more theorem is this, more stronger like that. For null recurrent, for null recurrent state, state y, this not only the limit, actually this, that each term, that sequence goes to 0, that limit n tends to infinity, that p n xy tends to 0. And this is stronger result. If some, this sequence tends to 0, then this summation divided by n, that's called Caesar sum, that Caesar sum also tends to 0. But the opposite, it may not be true. Caesar sum tends to 0, that the sequence may not be goes to 0. So for all x belongs to s. But this proof is again omit. This basis is very hard, very difficult. So it's omit. So why this is a stronger result? Because we know if n tends to l, what we know in the real analysis, the result from real analysis is this: if some sequence that an tends to 0 or tends to in L, say, not only 0, as n tends to infinity, then the Caesar sum is this a1 plus a2 by n, that also tends to 0. That you know, but the converse is not true. If the sum tends to 0, that sequence may not be converged also. So that's why this is more stronger result. Let's say each term actually goes to 0 as n tends to infinity. So starting from x is visit y after n many step, that probability goes to 0 for non-recurrent. So that's why it's called null recurrent. It will visit that y with probability 1, but as n tends to infinity, that probability goes to 0. Again, one more theorem, we without proof, let x be a positive recurrent. Now this is for the previous one for null recurrent, now it is for positive recurrent state. And suppose that x leads to y, then x is positive recurrent. Sorry, y is positive recurrent. Say positive recurrent state leads to a positive recurrent state. Proof again omit. Some difficult, these are difficult proof. So we omit this. One more theorem. Next theorem we will give the proof. The note is one more note that if C is a irreducible closed set, then either every state in C is transient. We know that if one state is transient, every state is transient, irreducible, since it is irreducible. And if one state is taken, then every state is taken transient, or every state in C is null recurrent, or every state in C is positive recurrence, because is one positive recurrence state leads to some state, then it is also positive recurrent. So either all the states are recurrent, positive recurrent, or either all the states are null recurrent, or all the states are transient. So basically there are three type of things: null recurrent, positive recurrent, and transient. Now next theorem is a very important theorem. This is if C is a finite closed set, the set is finite and closed. We know if it is finite closed, then it is a recurrent. That's all set is recurrent states. Then, so we know this all states are finite closed set. It may not be irreducible, just closed set. Then what happens? Then C has, we know then C has at least one recurrent state. If it is finite, at least must be, since the closed, must have one recurrent state. But here the theorem said that C has at least one, not only the recurrent state, at least one positive recurrent state. Positive recurrent state. May not be the all. Some may be positive recurrent, some may be transient, some may be null recurrent, because it is not a irreducible one. If it is irreducible, so what happens? So if C is a irreducible, finite irreducible closed set, then the all star states are positive recurrent set. And it is obvious because it is a finite, so every state coming in the infinite many times and is visit infinite many times, and not only the infinite, as n tends to infinity, this cannot be goes to 0. Because for large n also the state must be somewhere in the finite, since it is finite. So what is the proof? This is the basic idea. So what proof must be rigorous. That proof is like that. We know the sum of all y belongs to C, that P starting from x goes to y at the m state, that must be 1 for any state y, x in C. Now this what this implies? That implies that 1 by n, sum of our m equal to 1 to n, that y belongs to C, that m state probability, transition probability, that is also 1, because if this sum is 1 and then take the sum equal to 1 to n, m equal to 1 to n, that is n, and n by n is just 1. This is true for all n. Now we just interchange the summation, because C is finite state, the set C is finite, we can interchange that thing. That is the idea, we can interchange that. Because that C is finite. Since it is finite, we can interchange the finite sum. If it is infinite, there is a problem. Now what is this? This is nothing but that is G n xy. So it is sum of our y belongs to C, 1 by n, or you can just write G by n. G n xy, this is actually the sum of our m equal to 1 to n, the m transition probability from x to y, that divided by n, that is 1. Now what we have to show? We have to show that there is at least one positive recurrent state, and that must be true, because now if all these states are null recurrent, what happens? Now, if possible, let each state in C is transient or recurrent, then what happens? Or recurrent, if it, or null recurrent. If it is transient or null recurrent, then what happens? Then what happens? Then 1 equal to, we know that we already proved that 1 equal to this thing. So that must be limit. If you take the limit, the limit is also 1. So limit n tends to infinity, that sum is 1, because this is itself 1, so limit must be 1. Limit of 1 is 1. Now we just interchange the limit. You can easily interchange the limit. Why? Because it is finite. Again, since it is C is finite, the summation is finite summation, so we can put this limit inside. So it is limit n tends to infinity, G n xy by n, that is 0. But this is 0 because we know that limit n tends to infinity, gn xy by n, that is 0 for null recurrent as well as transient. So 1 equal to 0, the contradiction. There is a contradiction. So this contradiction shows that that must be a positive recurrent state in a finite closed set. And it is useful, then all the states are positive recurrent. Now some note. Let C be a finite irreducible set, irreducible closed set of states then every state in C is positive recurrent, because there is at least one positive recurrent state, and this is, since it is irreducible, all the states leads from that state, so every state is positive recurrent. Number 2, an irreducible Markov chain having a finite number of if the Markov chain has a finite number of state, that means that all states of this Markov chain is positive recurrent. So the chain is also itself positive recurrent. The chain recurrent means every state is recurrent. Chain transient means every state is transient. Chain positive recurrent means every state is positive recurrent. So it is a finite number of states. That means that Markov chain, and irreducible Markov chain having a finite number of states is positive recurrent. So the chain is also itself positive recurrent. Number 3, a Markov chain having a finite number of states has no null recurrent state. Why this is so? Because if there is a null recurrent state, then the irreducible closed set containing that non-recurrent state, all the states are non-recurrent. But since this Markov chain is itself finite, that closed set must be finite. But this closed set has all the states are non-recurrent. That can't be true, because at least there must be at least one positive recurrent. So there is a contradiction. So a Markov chain having the number of states having finite number of states. Sorry, having finite number of states. Then there has no null recurrent state. Maybe transient state, but no null recurrent state. It may have transient state, but it can't have any null recurrent state. So we stop this lecture here, and next we state the bounded convergence theorem, and from that we prove some result and then give some example.